today we will see that how to deal with the properties of pure substances for identifying various thermodynamic states. What we have discussed earlier, to summarize that, we can say that properties are signatures of states, right. So, if you have a thermodynamic state, the thermodynamic state is designated by a combination of thermodynamic properties. If it is a simple compressible pure substance, it requires two independent intensive thermodynamic properties to specify the state of the system. So, condition of a system designated by its properties is called as the state of the system. So, when we say that, it means that if we can identify two independent intensive thermodynamic properties, we will be in a position to identify the state. That means all other properties whatever are relevant can be obtained from that. How do you obtain those properties? So, this is a very important concept to realize, that in school level most of you have done some kind of thermodynamics, where the properties were dictated by the ideal gas type of relationships. For example, for an ideal gas you can write PV equal to nRT. Okay. So, when you write that, what you are essentially describing is an equation of state where pressure, volume and temperature are related with each other. So, that means if you specify pressure and volume, the third property which is temperature is automatically defined by that equation. In many practical scenarios, the substance is not an ideal gas. When it is not an ideal gas, you cannot use, maybe in certain cases for non-ideal substances such equations of states are available, some are empirical, some are not, but in general such a simple equation of state which is typically like the ideal gas equation of state will not work for a substance which is more practical than an ideal gas. So, if it is like that, then how do you determine the properties? That is an important question, and that is an important situation, a very challenging situation that most of the students face in working out problems in thermodynamics where the properties are not the properties of ideal gases. So, what would you do? So, for such a scenario, we either have an equation of state which is more complex than the ideal gas equation of state, which defines the relationship between properties. That means, if you give two independent intensive properties as input, the third property will come as an output from that equation, maybe a complex equation, but where pressure is a function of temperature and density in some way or the other, or temperature is a function of pressure and density in some way or the other. So, these things are there. However, it is very convenient if all these data points for a particular substance are summarized or tabulated in the form of thermodynamic property tables. And today we will try to work out examples where we will illustrate how to use the thermodynamic tables. I would like to emphasize here is that thermodynamics education has gone through a shift of paradigm. Traditionally, and even when I was myself an undergraduate student, we used to follow the property tables very judiciously to identify the state points. However, over the past few years there has been an emerging trend of using computerized data tables. That means, if you give the properties or give two independent properties as input, the third property which is a function of those two properties will come out automatically as a part of the software instead of having to look into the table. So, that kind of paradigm has come up recently. It does not change the concepts in thermodynamics, but it changes the approach in which you may possibly solve a problem. So, in this course what we have designed is that we will consider both these approaches. So, one, the traditional approach where looking into the table is important, and I will tell you that there is a benefit of the traditional approach. The benefit of the traditional approach is that you can visualize very nicely that what is the physical state of the system. Is it a two phase system, is it a superheated system, is it a subcooled system? These things you can nicely visualize from the tabular information. The computerized system, the advantage is that despite the fact that it does not give you an easy visualization until and unless you plot using the computer generated data, you can work out problems relatively quickly and elegantly without making the toil of looking into the property tables in the hard form. So, there are advantages and disadvantages. I will not get into the debate of which one is a better method and which one is not so convenient. Both these approaches have their own merits and possibly some demerits also, and I will straight away start helping you out to see that to understand that how the property tables look and how the property tables can be used to solve problems. So, if you look into the property tables, there are property tables of various substances, and many of these substances are actually phase changing substances. That means, given a heat transfer to the system, we will see later on what is heat and all, but we can qualitatively understand that by transferring heat you are energizing the molecules of the system, and then the molecules from the liquid phase, for example, can go to the vapor phase, or from solid phase can go to the liquid phase. So, these kind of phase changing substances, their properties can be nicely tabulated in the form of a structured table. Why we are interested in such substances? Because water, one of the most common engineering fluids, is a substance of that type. So, properties of water are described or enumerated in the form of tables known as steam tables. So, I would like to explain you first that how the steam tables look and how to look into the properties through steam tables. So, before getting into the steam tables and how do they look, I would like to give you a conceptual description of what we are talking about. So, let us say that we are interested to plot one state point in a PV diagram or a TV diagram, whatever. So, when we are interested to, so let us say for example, this is T, this is V, temperature specific volume diagram. So, for a substance like water, you have a diagram like this, a dome shaped region below which you have the change of phase as you heat it from liquid to vapor. So, this is let me write it in symbols. So, on this side it is liquid, on this side it is vapor, and in between there is a liquid to vapor transition as you heat the material or heat the fluid. When you have your data point or a state point for which the temperature and pressure is beyond this, that is called as supercritical fluid, and that does not pass through this phase change process. So, the first question, that given a set of properties, where does the state point lie? Does it lie here, does it lie here, or does it lie here? This is the first question that you might be interested to answer before solving a problem. This is like step 0 of understanding thermodynamics. We have not yet started looking into thermodynamics, but this is absolutely essential for solving problems in thermodynamics. So, where is the state point lie? How do you understand that? So, to understand that, we can refer to a specific problem, and then we can try to solve the problem, and through that problem we will learn how to use the table. So, for that I will refer to this example problem. So, the problem is described in the slide, and we will of course share these slides with you as a part of supplementary material of this course, but you can note this problem down so that it helps you to do a pen and paper solution of this problem. So, let me go through the problem statement first. Water vapor initially at 3 MPa 300 degrees centigrade, which is state 1, is contained within a piston cylinder assembly. The water is cooled at constant volume until its temperature reaches state 2, which is 200 degrees centigrade, and the water is compressed isothermally to a state when the pressure is 2.5 MPa. Locate state 1, 2 and 3 on a TV and PV diagram. Determine the specific volumes at state 1, 2 and 3 and quality at state 2. This problem I will do in a very different way. So, I will give you the idea of how to identify the state points. You have to generate the data from the table, and this will be your first homework problem for this particular course. So, whenever there is a problem in thermodynamics, see, thermodynamics is many times a very challenging subject to students, because the problem solution is not very structured. Every problem has a different way of looking into it, but we can try to structure this to the extent possible so that it helps you out. So, first is water vapor initially at so let me look into the properties. So, water vapor initially at 3 MPa 300 degrees centigrade. So, state 1. So, the system, thermodynamic system is water. State 1, 3 MPa and 300 degrees centigrade. So, P1 is 3 megapascal, T1 is 300 degrees centigrade. Okay. Then the process from 1 to 2, what is the kind of process? It is given, it is cooled in a constant volume process. The process is such that V2 equal to V1. See, it is a control mass system where the mass is constant. So, if the total volume is constant and mass is constant, that means specific volume is also constant. We will discuss later on that why specific volume is considered to be such an important property instead of its inverse, which is density in thermodynamics. Why we use specific volume so commonly instead of using density? Of course, density is just inverse of the specific volume, so we could use the density also, but specific volume, why it is so convenient to use specific volume as a property and density not so much convenient while working out problems in thermodynamics. We will discuss about that. So, the process 1 to 2, V2 is equal to V1, and then this is the other information. Remember that we require two independent properties, because water is a simple compressible pure substance. So, we require two independent properties for specifying its state. So, what is T2? T2 is given as 200 degree centigrade. It is cooled from 300 to 200 degree centigrade. Then from state 2 to state 3, what it does? The water is compressed isothermally to a state 3. So, process 2 to 3 T3 is equal to T2, and which is 200 degree centigrade, and P3 is equal to 2.5 megapascal. What you have to do for this problem is simply identify the state points on a PV and TV diagram and maybe the processes, and determine the specific volume at 1, 2 and 3 and quality at state 2. Okay. So, let us try to look into this problem. I will do the initial problems very slowly, so that you can understand that how to solve these problems by looking into the property tables. State 1, 3 MPa 300 degree centigrade. Now, how can you tell whether this is liquid water, liquid plus vapor or superheated vapor? How can you tell this? So, let us look into the steam table. So, just look into the table which is given in the slide. So, the first portion of the table is saturated water vapor table. Okay. So, in the saturated water vapor table, let us look into the data of 3 megapascal. 3 megapascal is 3000 kilopascal. So, if you look here, you will see that the first column is pressure, second column is temperature. See, in the two phase region, if you define the value of pressure, the temperature is also defined automatically, because the saturation pressure and saturation temperature, they are unique functions of each other. So, when you have saturation pressure as 3000 kilopascal, its corresponding saturation temperature is 233.9 degree centigrade. You look it from the table. Okay. So, when you have this as 233.9 degree centigrade, what is your given temperature? So, let us write this. P saturation at T saturation at P1, what is that? It is 233.9 degree centigrade. Okay. Your T1 is greater than this. That means it has crossed the saturation temperature limit. This implies that it is in the superheated vapor region. So, when it is in the superheated vapor region, this table, which is the saturated water vapor table, you can see here, this saturated water vapor table will not work anymore. You have to consider the superheated table, but even if it is a superheated data point, your first check is from the saturated water table to figure out whether it is actually superheated or not. So, once you get that data, what you do is you find out, you look into the superheated vapor table. So, in the superheated vapor table, if you have the pressure as 3 MPa, which is here, or 3000 kilopascal, at 300 degree centigrade you get what is the specific volume. Some other properties are there, internal energy, enthalpy, entropy. Whenever we will require these properties we will discuss, but for this problem it is the specific volume that is required. So, state 1, so we can simply write that from superheated table, from superheated water table you have the specific volume at state 1 is 0.08114, 0.0811, say let us stop here, meter cube per kg. So, I will draw one of the diagrams, say TV diagram. So, state 1 is somewhere here, this is what you can visualize. From state 1 to state 2 you have V2 is equal to V1, which is this one, okay, and T2 is 200 degree centigrade. So, the question is it still in the superheated or it has come to saturated? What is the, on which line the point state point 2 will lie? If you draw a vertical line, somewhere on this it will lie. Because it is cooled it will be down, but the question is down where, beyond this line or below this line. So, for that again you have to look into the table at 200 degree centigrade. So, let us try to look into that. The saturated table, so 200 degree centigrade, so So, 200 degree centigrade, I do not have the data point with me here in this table, it is up to 100 degree centigrade it is given, because this is just a way of giving you an idea how to do that. So, at 100 degree centigrade for example, you have Vf and Vg. If it is in the two phase region at 100 degree centigrade, this is Vf where I have pointed the pointer, and this is what is Vg. So, if your V is between Vf and Vg, then it is in the two phase region. Similarly, at 200 degree centigrade you will have some Vf and some Vg. So, at 200 degree centigrade, so this table will be continued up to even higher temperatures. So, at 200 degree centigrade you have to look what is Vf and what is Vg. So, at 200 degree centigrade you have, so I have the data with me, I can tell you at 200 degree centigrade, this you can verify from the table, saturated table. Vf is 1.56 into 10 to the power 1.565 into 10 to the power minus 3 meter cube per kg, okay, and Vg is 0.12736. This is from saturated table. Okay. Now you tell your V is between Vf and Vg, right. So your V is 0.0811 which is in between these two values. So V2 is between Vf and Vg at T2. If that be the case, then the state point 2 will lie somewhere here in the two phase region. So what is the specific volume at state 2? It is same as V1. What is the quality at state 2? So V2 is x Vg2 plus 1 minus, this formula has been derived earlier in one of the classes, so I will not get into the details here, but you see the point that I want to raise is that it is for this reason that we use specific volume, not density. See, the specific volume of the mixture is a weighted average of the specific volumes of the liquid and vapor phases, not the weighted average of the density, right. So by using law of mixture, it is very easy to calculate the properties of mixtures. So here x2 is what? Mass of vapor at state 2 by total mass. So you have Vg2 and Vf2, these two, and V2. So from here you can calculate what is x2. Okay. So once you have calculated x2, so you can check this should be between 0 and 1, that means you have you are there in the two phase region. In the process 2 to 3 you have T3 is equal to T2 and P3 is 2.5 MPa. So now again you have to see at 200 degree centigrade or at 2.5 MPa, whatever, you look into the saturated table. So let us see that at 2.5 MPa what is the saturation temperature. So (2.5 MPa), so let us look into the saturation temperature at 2.5 MPa. So even in the superheated vapor tables, the saturation temperature is indicated. So 2.5 MPa is what? 2.5 MPa, just look into the superheated water vapor table. So 2.5 MPa or 200 degree centigrade, let us say 200 degree centigrade. So 200 degree centigrade, I do not have the data at 200 degree centigrade, but if you look into the 200 degree centigrade, you will have the saturation temperature at 200 degree centigrade. If you look into the property table, I do not have that part of the table, but I have the data at 200 degree centigrade the saturation pressure is 1.553 MPa. That part of the table I do not have at this moment, but this is your homework. So I have deliberately left that part of the table out. So I have only kept up to 100 degree centigrade, which you see here. You will have an extension of these up to higher temperatures. So at 100 degree centigrade the saturation pressure is 101.3 kilopascal. Similarly, from the saturation table at 200 degree centigrade you will get the saturation pressure as 1.553 megapascal. Now this P3 is greater than that means that it is in a compressed liquid state. So P3 is greater than P sat at T3. This means it is 3 in compressed liquid. So, compressed liquid in other case, in other words, is also called as subcooled liquid. What does it mean? It means that at 2.5 megapascal, whatever is the saturation temperature, this temperature is less than that saturation temperature. So, from that angle, from the temperature angle you can call it subcooled, from the pressure angle you can call it compressed liquid, all the same. So, at the state point 3 it will be in the fully liquid state, and from 2 to 3 it will be something like this, isothermal process. So, 1 to 2 like this and 2 to 3 like this. So, how do you identify state 3? 200 degrees centigrade and P3 as 2.5 MPa. Which table you should look for? Now, so we have looked into the saturated water table and the superheated water vapor table. There is a third table which is called as compressed liquid water table. So, at 2.5 megapascal, you see that you have a table at 2 megapascal and 5 megapascal. So, 2.5 you may have to interpolate. At 2 megapascal at 200 degree centigrade you have a specific volume. So, I am using this part of the board. At 2 megapascal 200 degree centigrade, the specific volume is 0.001156. Okay. Let us write it in one line, 0.01156. And at 5 MPa, see the table does not contain 2.5 MPa. At 5 MPa 200 degree centigrade, it is 0.001153. Okay. So, the question is at 2.5 MPa what is that? So, let us say that at 2.5 MPa it is V3. So, V3 minus 0.01153 by 0.01156 minus 0.01153, we are doing an interpolation. It is V3 is P3, which is the corresponding pressure is P3 equal to 2.5 minus the corresponding pressure is 5 divided by 2 minus 5, right. Y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1. We are interpolating the pressure versus volume data with y as volume and x as pressure. So, this will tell you what is V3. The answer to this is 0.01155 meter cube per kg. See, it is not always necessary to go through this laborious process. When it is state 3 and the temperature is around this 200 like that. So, water at 200 degree centigrade, liquid water, what will be its density? It will not be far from 1000 kg per meter cube, right. So, 1 by specific volume will be 1 by 1000 and it will be close to that. So, at least 0.01 sorry, this is 0.00 0.00115 not 01. So, this is 0.00, all another 0 is there, I have missed this, okay. So, 0.001153 0. These are all another 0 will be there. So, this mistake you can very easily detect because water density normally is 1000. So, 1 by 1000 is 0.001, right. So, another 0 will be there. So, you see that only in the 3rd, 4th, 5th decimal the values are changing. So, for all practical purposes, if you even do not look into the table, but just figure out that it is a compressed liquid, then you can easily say that compressed liquid means it is almost like the density of water under normal temperature. I mean from normal temperature to 200 degree centigrade, the density of water will not vary that much if it is liquid water, okay. So, this problem I have spent a lot of time, but I have tried to make sure that by looking into the tables how can you identify these state points, and I hope this was useful. From the next lecture onwards we will start looking into some more specific problems on properties of pure substances. Thank you.